Welcome PCS members and our friends to our today's PCS IBS seminar. It is a great pleasure to have with us today Professor Sarang Gopalakrishnan from Penn State, and I would like to invite our scientific host Dario to introduce our speaker. Please, Dario.
Yeah, thank you, Tilen. It's a great pleasure to have Sarang today for our weekly seminar. So let me introduce our speaker. So Sarang got his PhD in 2012 from University of Illinois at Urbana-Champaign. And after that, he had a couple of postdoctoral appointments, one in Harvard and another in Caltech. And after that moment, he moved to the City University of New York as an assistant professor, and finally is now still an assistant professor, or probably an associate professor, right? In Penn State.
Professor. I'm too lazy to get tenure.
Okay. Okay, so he's currently an assistant professor in Penn State University. So let me introduce a little bit the research topics of Sarang. So Sarang is generally interested, I would say, in many-body physics and in anomalous transport, among them, for example, many-body localization, but not only many-body localization, of course. And today he's gonna talk about some surprises, and we are looking forward for seeing these surprises in high-temperature transport. So Sarang, please, I think you can start.
Thank you very much, Dario. It's wonderful to be here remotely. I wish I had been able to actually make it in person. So this talk is going to be about high temperature transport. And this sounds like kind of a weird topic to be giving a talk about, because historically condensed matter physics emerged as a theory of things that happen at low temperature rather than high temperature. It's worth thinking about why historically people didn't care so much about high temperature transport, why this problem wasn't sorted by smart people like Phil Anderson in the 1960s, in the early days of condensed matter physics. So the philosophy that people of that era had, and that still dominates condensed matter physics, is to say, look, the full many-body problem is obviously completely intractable, but one way to make it to reduce it to something tractable is to say the system is almost everywhere in the ground state, except you have every now and then a few excitations floating about. And that allows you to treat the excitations, which could themselves be very complicated, like in the fractional quantum Hall effect. But whatever they are, there's a dilute gas of them. And if you want to understand transport, you just need to understand the properties of the excitations, then you're done. So that's one line of thinking that said, focus on low temperature where the excitations are dilute. A second line of logic goes even further back, and it just says, at high temperature, you don't even know what your system is because there are too many fluctuating degrees of freedom to keep track of. So for example, your system is in a box. The box has black body radiation. You might worry that you have to keep track of those degrees of freedom as well. At low temperature, they're all frozen out. You have a well-defined Hamiltonian. So once again, there's not even a starting point to really talk about high temperature physics. And anyway, the third line of logic would be to say that all the really cool, surprising physics, things like superconductivity, happens at low temperature anyway. That's where your experiments are going to see an interesting signal. And so that's where you should be looking. And so all of these perspectives converge in saying that what you really should do is you should theoretically compute and experimentally measure thermodynamics and linear response transport at low temperatures. And that's great for conventional bulk materials, but increasingly our current day experimental capacities go beyond that. And so many systems nowadays are in this regime where there's objectively low temperatures. So if you look at the actual temperature as a number, it's, I don't know, microkelvins or millikelvins or whatever, depending on the platform. So you don't need to worry about the system being objectively hot and full of thermal phonons and black body radiation and things like that. you really can think about it as an isolated system that's got a well-defined Hamiltonian, and the system state is at high temperature or high energy with respect to that well-defined Hamiltonian. So what are these systems? Well, the first is, of course, any candidate quantum computer, because a candidate quantum computer needs to, in order to do a computation in the gate-based paradigm, you need to go far away from the ground state of any Hamiltonian. You need to go to arbitrary states in Hilbert space. So it's superconducting qubit arrays or ultracold atoms and so on. This is sort of part of the core functionality of these platforms. And so certainly you can study the kinds of question where you're looking at an isolated system at high temperature in these platforms. Another set of platforms is conventional materials that are probed either using ultra-fast laser pulses, so the relaxation hasn't had time to happen. The system is still isolated because the phonons are frozen on the relevant timescales. So that's what, for example, these nice time-dependent Floquet ARPES studies show. A totally different context is that of frustrated magnets. In a frustrated magnet, what happens is that the classical ground state is highly degenerate, and therefore that means that even at quite low temperatures, you have a lot of entropy because you still aren't resolving the splittings of this ground state manifold. You're working in a finite entropy space. So with all of these systems, you can study what happens at nominally high temperature, which is to say, for states in the middle of the spectrum of the Hamiltonians that are describing these systems. And so for these states, you don't really have the principles that we used to in condensed matter physics. There's a lot of entanglements. You can't use tensor network methods so well. There's also not any notion of elementary excitations that are dilute because everything is dense. There's not sort of you're not linearizing about a ground state or something like that. And so the standard paradigm of condensed matter physics doesn't work. And you might say, well, this seems bad. Are we stuck? Do we have any way of describing these experiments? The things that I told you, you might find less shocking if you've thought about something like water. So remember that water is a liquid that's a very strongly interacting fluid that's incompressible. There's absolutely no hope of describing it in a microscopic way. And if you ask me to do a calculation that tells you, for example, what the boiling point of water is, I would have no idea how to do it, nor would anyone else. But that doesn't bother us because we know that's the wrong way to think about water. Those are wrong questions to ask. If you want to understand the things you really care about with water, like, for example, how does it flow in a pipe, what are its interesting physical phenomena, you use a totally different perspective. And this totally different perspective is that of hydrodynamics. With hydrodynamics, what you do is you say the system rapidly relaxes to some local equilibrium state. And so essentially everything that's not a conserved quantity, or in some cases of symmetry breaking in Goldstone mode, anything that's not symmetry required or conservation law required to be slow is fast, and in fact relaxes instantaneously. And on this assumption of instantaneous relaxation, what you can do is you can say, okay, I'm just going to write down equations of motion for whatever slow modes remain. And I can do that systematically in a gradient expansion. And then I'm done. I don't really have anything else I need to do because now I have some low dimensional problem, which is differential equations for a few conserved densities. And I can find the hydrodynamics of those quantities. The thing I don't get, of course, is I don't know how to microscopically compute the coefficients that go into that hydrodynamics, but maybe that's not what I care about. Maybe all I care about is the way things scale with time and space. And that is easy, at least for this case. And it's actually, it's easy in some nominal sense of water, but of course, water is described by Navier-Stokes equations, which are very rich and give you things like turbulence. If you put the system on a lattice, momentum and current are not conserved. And so hydrodynamics in one-dimensional lattices is very simple. All you ever get is diffusion of every conserved mode. And so that's the prediction. And that would say, if that prediction were correct, then high temperature transport would be boring. You can ask, well, is it in fact boring? Let me very quickly try and explain what I mean by something equilibrating. So in quantum mechanics, nothing actually, it's a reversible of theories. There's no strict notion of equilibration, but what's meant in the quantum mechanics of isolated systems, when you talk about things equilibrating, is it's a claim about local observables. That's two-body observables that are local, and you ask about their expectation values in the state as a function of time, and you say that these expectation values don't really care about the details of state. And so what happens is that your initial state that's out of equilibrium is out of equilibrium because some very complicated phase relation between all the eigenstates, that energy. But over time, that phase relation is lost, and the system becomes effectively thermal, in the sense it becomes a random phase superposition of these eigenstates. So it's effectively a mixture of these eigenstates, and so that all the eigenstates look locally the same. And so a mixture of them is just like any one of the eigenstates. There's a mixture of like 10 pounds of sand and 2 pounds of sand is the same as a mixture of 9 pounds of sand and 3 pounds of sand. It's like you're mixing things that are identical. You don't care about the proportions of mixing them in. So because of that, you have this effective notion of thermalization where local observables that are simple seem to go to equilibrium, even though, of course, the global state of the system never approaches an equilibrium state, because quantum mechanics is a reversible theory.
Sarang, can I just interrupt shortly?
Yeah, go ahead.
What do you mean by local observables?
What I mean by local observables, in some technical sense right now, I mean, I'm going to be very restrictive, and you can ask, and probably too restrictive, but what I claim is that I'm imagining a system in the thermodynamic limit. And when I say it's thermodynamic limit, I mean that it's Hilbert space, a tensor product of a bunch of Hilbert spaces that are local. And in this tensor product, I'm talking about observables that have finite support. So they're identity except on a finite number of sites.
That's very abstract. Can you give a more physical way of what kind of systems will fall into this category?
So if you think about a spin chain or a system of interacting fermions, I'm talking about observables that involve a finite number of spins or involve a finite number of creation and annihilation operators for the fermions.
Right, but what I probably meant is, do you have to make some assumptions about the system itself as well in order to start then focusing on these local observables? Because locality always assumes that you have some space in which you operate. Do you assume some kind of short-range interaction between some?
No, I don't. When I define thermalization, that's why I was talking about tensor products. I assume that there is some tensor product structure on the global Hilbert space. So that means either that I have some notion of what it means to have few spins or what it means to have few fermions. But I don't assume anything about space yet.
You could, in principle, also allow for long-range interactions between these spins, for instance. Is that correct?
Yeah, for eigenstate thermalization, it doesn't matter, right? So for eigenstate thermalization, all that matters.
No, I'm not saying it doesn't matter. I'm just saying that the notion of local observables, so locality.
There are various notions of locality, and for now, I'm restricting to a notion of locality. It's sometimes called K-locality, but basically what it means is, if you think in terms of fermions, I have only finitely many annihilation operators and finitely many creation operators, and I take the system size limit to infinity. I
see.
So that's the sense in which ETH is formulated. You can also add spatial locality on top of it, but it's not important.
Okay. So say
For
two-body
hydrodynamics,
interaction.
it's actually very important, right? For hydrodynamics, I do need spatial locality because I want to write down gradients. And
Right.
gradients make no sense without spatial locality. But for this slide, I don't need spatial locality.
Okay, thank you.
Okay. But yeah, so thank you for that question, Sergey. So anyway, so that's eigenstate thermalization. And I said it doesn't really require spatial locality, but of course, for hydrodynamics, I do need some notion of things moving out in space. And so I do need spatial locality to talk about hydrodynamics. And so in hydrodynamics, what I say is that even before a system becomes completely thermal, it becomes locally thermal in the sense that if I chop it up into blocks, the spatial blocks, each spatial block looks like a thermal state locally, even though the global system isn't yet thermal. Okay, and so the point I'm going to make, though, in the very next slide is that thermalization either doesn't work or works extremely slowly for an enormous range of systems that are realized in present-day experiments. Most of these examples involve cold atoms, but you can see long-lived excitations that fail to thermalize even in solid-state systems like electron gases. The basic failure mode of thermalization in these far from equilibrium systems is that even if the system is at finite energy density, even if it's very far from the ground state, it still has a lot of excitations, and they're all long-lived. And this is the long-lived character is what makes hydrodynamics break, because hydrodynamics assumes that everything that's not a conventional conserved quantity like energy or density is relaxing rapidly, and that assumption just fails in this variety of systems. On the other hand, they're also at finite density, so you can't use the ground state reduction. You can't say that it's just individual elementary excitations. So this requires a sort of approach to doing condensed matter physics that's different from either the standard low temperature approach or the standard high temperature approach. And so we still don't have a general framework for this, but the rest of this talk, I guess, is meant to sort of hint at a way of thinking about at least some of these systems. And so one more comment I want to make is that even though most of this talk I'm going to talk about linear response, in the actual experiments on cold atomic systems, you can measure a lot of things that a traditional condensed matter physicist would say, oh yeah, that's not really observable at all. And so that allows you to study things like, for example, endpoint correlation functions where n is the large number, or full distribution functions of particles in a many-body system. So the various things you can measure that aren't really few body observables. So to get back to, I guess, the question Sergey was asking, it's completely unclear to me to what extent eigenstate thermalization even applies to quantities like instantaneous snapshots of all the atoms in a system. They're not few body observables, not spatially local. So, okay, I mean, what can we learn by looking at these things? Anyway, that's a general question, which I won't have a lot to say about in this talk, but I think it's an important question for you to think about. Okay, so in the rest of this talk, I'm going to survey some work that we did over the past few years on basically a simplest model where you can really talk about long-lived quasi-particles at finite energy, and about questions like transport at high temperature, and I'm going to focus, I think, mostly on the very first bullet point here, which is surprises in even linear response transport in high temperature phases. I might say a couple of things about what happens beyond linear response. I just want to flag that there's an essentially identical or an essentially parallel story I could have told about strongly disordered systems, but today I'm not going to talk about those. I'm going to talk about clean systems, but many of the issues that arise are exactly parallel. And once you understand one class of systems, the other class becomes pretty simple to think about. Okay, So now let me quickly explain what the big deal is, what the puzzle is with linear response at high temperatures in the XXZ spin chain. And to explain that, I need a wee bit of background, which is what linear response means. So when I talk about linear response in many body systems, I mean linear response in the sense of the Kubo formula. I assume most of you have seen this before, but the Kubo formula is this very nice fact that relates the rate at which an injected current dissipates to the rate at which the sort of self-generated fluctuations of the current dissipate. So it's really a bedrock result of statistical mechanics, and it allows you. It's very useful because it allows you to stop thinking about how exactly you're probing the system. And you say if you're measuring the conductivity, you don't need to put in anything. You just need to measure this two-time correlation function of the system itself. So it's an intrinsic property of the system, not a property of the probe. So the basic expectation in a lattice system is that conductivity should be diffusive. And what that means is that if you put in a current, let's say you're thinking about the Drude model of electrons, that means you send a bunch of electrons moving to the right, and they keep moving to the right for a while, but then after some time, they hit scatterers, they hit impurities, and then they backscatter and they start moving in random directions. So the current after a certain amount of time is uncorrelated to the current you sent in, and that decorrelation time is the mean free time, and the conductivity is if you think about it, the DC conductivity is just the area under this curve, and so it's finite. The corrections that are important, your long time tails, but I won't talk about them. They're not relevant for my purposes in this talk. The two other kinds of behavior that you often see in many body systems, and they're both in some sense associated with breakdowns of thermalization. One type of breakdown of thermalization is when you have ballistic transport. It doesn't really have to be a breakdown of thermalization. It's just the existence of an exactly conserved components of current. So when transport is ballistic, what that means is that the current doesn't actually decay to zero. Fluctuations of the current are infinitely long-lived. So this would happen, for example, for water flowing in a perfectly smooth pipe because the momentum is conserved, and so the momentum cannot relax, as the current cannot relax. And so in this case, there's this notion of what's called the Drude weight. So because the current doesn't relax, the conductivity is a Fourier transform of this guy, has a delta function at zero frequency that tells you how much the current is conserved, and also has a bunch of stuff that decays in principle, and the area on the decaying part of this curve is the regular part of the conductivity. Another type of standard behavior is localization. In the case of localization, at least the way I like to think about it is you imagine your system divided into a bunch of isolated boxes. In each box is sort of closed. And so you put in a current, so you send all the particles in a box moving to the right, and then after a while they hit the edge of the box, and then they don't just decorrelate, they have to bounce back. And so that means that the current actually decorrelate, it's anti-correlated with itself at later times. And it needs to be that way because we know the DC conductivity has to be zero in a localized phase. So that's localization. And then between these three types of behavior, you have two intermediate behaviors that are particularly interesting, those superdiffusion and subdiffusion. Superdiffusion, the area under this curve is infinite, but this value actually decays to zero at late times. In subdiffusion, you have this funny power law behavior, which I won't have much more to say about this talk. So these two behaviors are interesting because they involve typically anomalous power laws, and also because unlike the behaviors on the upper row, they involve things happening, non-trivial things happening at all time scales. Whereas in superdiffusion, this current is not decaying, it's decaying in a scale-free way. And subdiffusion, the conductivity is approaching zero in a scale-free way. And both those cases, that means there's some kind of self-similar structure, some kind of multiple scale structure to the dynamics of the system. And that makes it interesting from a many-body physics point of view, because it's not just like there's one process and it's done and you're over, as it could be in the upper row. Okay, so why did I give you this catalog of possible transport behaviors? Because if you take the very simplest model you can write down and simulate numerically, and compute the very simplest thing, which is the conductivity, and you plot it versus these two parameters, the disorder and the anisotropy, you find that basically every possible transport behavior outlined is already evidenced in the simplest model that I could write down. And so this means that, unusual transport is kind of ubiquitous in many body systems at high temperature. The rest of this talk, I'm going to be somewhat specific and stick to the y-axis of this curve. But the story of what happens when you move horizontally across this curve is, of course, the story of many body localization, which at least some people in the audience I know care about and have made important contributions to. So on the y-axis, this model is integrable, and integrability is going to be the focus of what I'm going to say next. The thing about integrability is that people find it intimidating at first, but they shouldn't, because it's actually just kinematics. It's particularly the kinematics of one-dimensional scattering. So if you imagine trolleys on a frictionless track, they collide with each other, and when they collide, they've got to bounce off and go back up the track. There are two unknowns, which are the two final velocities of the trolleys, but there are also two constraints on those unknowns, because collision is elastic, so momentum is conserved, and kinetic energy is also conserved. And these two constraints fix the two unknowns, such that the only thing that can happen is that these velocities can get exchanged between the trolleys as a result of the collision. So if the velocity is just permuting around among the trolleys, then the total set of velocities in the system is conserved under two-body collisions among trolleys. And so that's fundamentally what it means for the model to be integrable. It means that there's some notion of a velocity-like distribution that is conserved. Normally, you'd say that many body system is not integrable, because you also have to include three-body and four-body collisions, and those are not constrained by this counting. But in many cases of interest, like the Heisenberg and Hubbard models, three-body collisions factorize, and the model is integrable. So three-body collisions sort of can be written consistently as a sequence of two-body collisions. Okay, and as you all know, this doesn't work in two dimensions, because you have more unknowns than constraints. And so if you try and hit a pool ball, it doesn't necessarily go exchange velocities your cue ball. Instead, collisions can randomize velocity distributions. Okay, so integrable systems are exactly solvable. And that you might say, okay, that's great. Why don't we just go exactly solve them? Why do we need any kind of physical picture to understand what they're doing? It turns out that the exact solutions, or the fact they're exactly solvable, should really be stated with a bit of an asterisk, because in terms of the many-body spectrum, the eigenvalues are easy to extract. In terms of the occupations of these fictitious quasi-particle objects. But on the other hand, the eigenstates in any physical basis are almost impossible to extract. And so the thermodynamics of the system in large part only cares about the eigenvalues and the occupation numbers of various eigenstates. It doesn't care about the wave functions of the eigenstates. So that's easy. Thermodynamics is easy. But on the other hand, anything that involves the matrix elements of physical operators, which do involve the eigenstates, is almost impossible to compute. And so for many years, we're sort of stuck, because all you could do with the Kubo formula was implemented numerically, and the numerics that's beta-ansatz assisted is not so much better than just brute force exact diagonalization numerics. So the big discovery that Ben Doyon and co-workers made a few years ago was that you could use the quasi-particle picture or generalized hydrodynamics to express these hard problems in terms of easy problems. And so in meme format, that's sort of what happened. You'd go from like thinking about these rather nasty functional determinants, think about trolleys in a track. And so that's going to be the basis of the results I'm going to present in what remains of this talk. But one basic conceptual point I want to make about this trolley on a track picture is the way you do the bookkeeping. So if you try to keep track of the velocity of the green trolley, then you'd have a really hard time, because each time the green trolley undergoes a collision, its velocity gets randomized essentially, because its new velocity depends on the old velocity of the thing it collided with. So that's a terrible way to do the bookkeeping. A good way to do the bookkeeping is to define this notion of quasi-particles. And the quasi-particles jump from one trolley to the next when a collision happens, but they always retain the same velocity. So we're always moving ballistically in a particular direction. And all that the collisions do is they give these horizontal shifts. And so they, if you think about it at the mean field level, they normalize the velocity. But they also crucially give fluctuations to the velocity, and these fluctuations are going to be important in what follows. A bit of history here. The first person who really started taking this quasi-particle picture seriously was Sachdev, in a series of really important papers in the 1990s. But what Sachdev and his co-workers didn't quite appreciate was that you could do this at arbitrary temperature and arbitrary states if you use a bit of thermodynamic beta-ansatz input. And that's something that was realized by Doyon and co-workers and by Bertini and co-workers in, I guess it's just about 4 or 5 years ago now. And so the quasi-particle picture has proved incredibly productive to think about transport and even things like entanglement growth in integrable systems. But one thing that you might say, just looking at this, is that the quasi-particles are ballistic. And so you might think almost everything you explain in terms of quasi-particles has to be ballistic also. And so if you take that perspective, you might say, okay, you know, this is this behavior of the XXZ model is very counterintuitive, because instead of being ballistic everywhere, what you find is energy transport is ballistic, but spin transport goes from being ballistic to being diffusive as you go from the easy plane regime to easy axis regime. This transition in the spin transport coincides with a transition in the zero temperature phase diagram, where the model goes from being gapless to being gapped. You might say, okay, that's completely irrelevant, because we know that in one dimension, any finite temperature is the same as being at high temperature, because the model is local. And so, you know, why would the system have any recollection of this ground state phase transition if you're looking at finite temperature? That's one question you might ask. The other question you might ask is, why is anything other than ballistic transport ever possible in an integrable system? And just to summarize what our understanding of this phenomenon is nowadays, the basic point is that this phase transition happens, and it coincides with the zero temperature phase transition, because in an integrable system, quasi-particles don't decay. And so even if you're at high temperature, so the quasi-particles at high density, they retain the character or some aspects of character that they had as elementary excitation. So for example, in the easy axis regime, the ground state is an Ising type ferromagnet or antiferromagnet. And so the excitations are domains or domain walls. And so they have one kind of behavior. In the easy plane regime and the Heisenberg point, the excitations about the ground state are Goldstone modes. And Goldstone modes have a totally different type of behavior. So in some sense, what this phase transition is it's a transition between a dense gas of magnetic domains and a dense gas of highly normalized Goldstone type excitations. And so that's why the transition happens. And the fact the transition happens in one dimension at high temperature is, of course, allowed because it's not a thermodynamic transition, it's a purely dynamical transition. Okay, I've been going slower than I'd have wanted to, so let me just very quickly explain what happens in the easy access phase, and then I will probably leave the rest for questions and further discussion. So in the easy access phase, it's the easiest way to start thinking about this. You take delta to be very large, and so to begin with, you just treat what happens at infinite delta. At infinite delta, the Hamiltonian is just dominated by the ZZ interaction. And so the eigenstates are bit strings of ups and downs. And the energy of each eigenstate is just given by counting the number of domain walls in that eigenstate. And so you can go from, you can transition from one state to another in this regime in perturbation theory and the hopping, if by doing so, you maintain two conservation laws. The first is you cannot change the number of domains, the number of domain walls, because that would cost energy and you don't have energy to pay. The second thing you can't do is you cannot change the total number of upspins because there's an exact U1 conservation law in the model. So domains can't grow or shrink, unlike the Ising model. All that a big domain can do is it can collectively move all at once, and it can only do that at very high orders in perturbation theory, so it's basically immobilized. And so domains of every size are sort of well-defined quasi-particles, and each domain is sort of its own species of quasi-particle. And in this large delta limit that's strongly anisotropic, the only type of domain that's actually mobile is the elementary domain, which is a single magnon. And you think about a single magnon as being an upspin in a sea of downspins, or vice versa. And the key dynamical thing that happens in this problem is what happens when a single magnon comes and hits a domain wall. And that's what I've illustrated here. So this is my magnon, my black spin moving through a white domain. And it just keeps moving through, not encountering any dynamical obstructions until it gets all the way to the nearest domain wall. Now here you have a problem because the black spin can't keep moving, because if it moves one step further, you'll destroy two domain walls, and that's no good because lowering the energy is just as bad as raising it. On the other hand, what this magnon can do is it can transmit in a sort of Andreev-like process through the minority domain. And as it does that, it propagates through this black domain as a white spin, and then it pops back out at the end as a black spin propagating through the next white domain. So the two observations I'd like to make based on this, the first is that that magnons don't actually carry any magnetization in a state with an equal number of up and down domains, because half the time they're moving as black spins in a white background, half the time they're moving as white spins in a black background. So on net, they don't carry any spin. The second thing I want to point out is that, and so this is why spin is not transported ballistically, because even though the magnons move ballistically, the magnons are neutral and everything else is just frozen. So why is there diffusive transport? There's diffusive transport because these big frozen domains undergo Brownian motion because they keep getting bombarded by magnons coming in from left or right. So over time, they sort of jitter about, and that gives you diffusion, and that's the origin of diffusive spin transport. So there's actually a kind of nice, simple dual perspective that lets you understand the diffusion in a quantitative way. and it goes like this. So your magnon is moving through a region. Let's say you wait for time t. Your magnon only sees a region of size proportional to t because it's moving ballistically. And in this region, the net magnetization is not exactly zero. It's offset from zero by thermal fluctuations that are square root in the system size that the magnon can see. And that's just 1 over square root of t. And so net magnetization is of the magnon is 1 over square root of t. And so if you want to understand how much magnetization got transported, a magnetization 1 over square root of t got transported ballistically over a distance t, and the t and the square root cancel, and that gives you the magnetizations moved by an amount that's proportional to the square root of t, and that's where you get diffusion. So basically, you get diffusion in this model because you have ballistic motion of the magnons, but the magnons are almost completely depolarized as they move, and so diffusion is like the residual polarization of the magnons, which comes from these thermal fluctuations. I gave you the theory for the infinite delta limit where it's simple, but you can also extend it using a little bit of Bethe-Ansatz data to arbitrary delta, arbitrary anisotropy is bigger than 1, and you get this closed form expression that has 2 important features. First is it goes to finite limit at large delta because the magnons are never frozen out. It also diverges as delta goes to 1 because as delta goes to 1, all the bound states, all the domains become pretty mobile. One point I'd like to make about this result is that it's, as far as I know, the only exactly known diffusion constant for a strongly interacting or even any general interacting Hamiltonian. A couple of immediate consequences. The first is that diffusive transport came from the exact cancellation of up and down domains. If you create a net magnetization with, like, let's say, a weak magnetic field, then you're going to have slight failure to cancel. And so it's going to give you these faint ballistic transport features, which become fainter and fainter as you approach half filling, because the cancellation between up and down domains becomes better and better. And so at general filling, you have this coexistence of a ballistic feature and an almost but not quite diffusive feature. It's like slightly super diffusive. A second interesting consequence of this is what happens when you break integrability. When you break integrability in a system with ballistic transport, what that gives you is that it gives you a lifetime for the quasi-particles, gives you mean free time, and so your delta function through the peak becomes a Lorentzian. So you get diffusive transport. What happens if transport was already diffusive, like in this gap-XX Z-spin chain? One thing you might guess is that not really a whole lot happens because model is already diffusive. What can happen? Maybe the diffusion constant changes by a bit. A slightly crazier thing you might guess is that you might take this argument that I made in the previous slide very seriously, that that the diffusive transport comes from ballistic motion and almost complete depolarization. And so diffusion is a result of an imperfect cancellation between these two things. If you take this perspective and then you make quasi-particles diffusive, then what you're going to find is ballistic goes to diffusive, and this near cancellation takes you down from diffusion, actually the subdiffusion with the space-time scaling position goes this time to the 1/4 power. And in fact, what you see in the experiment, or what you see in numerics, is that you see that there is subdiffusion for this very long time window, but it eventually crosses over diffusion with a diffusion constant that's actually independent of the strength of the integrability breaking perturbation, but does depend very strongly on the anisotropy. I don't really have time to go into the details of where the diffusion comes from, where this eventual diffusion comes from, but the short explanation is that on very long time scales at finite delta, the magnon picture breaks down because all these magnons can decay or can merge with each other into frozen domains. The frozen domains can split up into magnons and so on. Okay, so the conductivity of this model has this feature when you break integrability that it goes from being order 1 at large delta to being order 1 over delta. So there's a discontinuity as this integrability breaking perturbation strength goes to 0. And this means that numerical attempts to understand diffusion in these models are really delicate, because if you break integrability and you try and restore it by taking the integrability breaking to 0, you get the wrong answer. Okay, so this is all I wanted to say about the easy axis phase of xz, which is that you get diffusion from this almost perfect screening of magnons, and this gives you an exact formula for diffusion constant. If you go away from half filling, you get a bit of ballistic transport. You still have this big diffusive background that shows up in the structure factor, and that if you break integrability, you get a subdiffusive regime. So I just want to make like one very quick comment about the isotropic point. That's the Heisenberg point, and that's that essentially the same argument goes through that I made in this large delta phase, except that instead of using the properties of domains, you've got to use the properties of Goldstone modes. And the key thing about these Goldstone modes is because you have a non-abelian SU2 symmetry, the Goldstone modes about the ferromagnet are quadratically dispersing, and the quadratic dispersion of the Goldstone modes together with some counting arguments, which I don't have the time to actually go over in this talk, rather directly give you this dynamical critical exponent that's measured in numerics and has also now been measured in experiment. I just wanted to flag that that the theory we have of the tree has exponents, not just a scaling theory, it also gets the prefactors right. It also correctly predicts that the same scaling exponent occurs in basically any integrable spin chain that's invariant under a non-abelian Lie group symmetry. And finally, it's been seen in experiments, and so yeah, let me skip that. And so the thing that's a bit mysterious right now is how do you go beyond the exponent for transport? How do you compute this full scaling function, this full structure factor at the Heisenberg point? There are fairly strong numerical indications that this belongs to the Kada-Parisi-Zhang universality class, but as far as I know, there's not a really clear and convincing explanation of why that is. Yeah, and so in order to study this, you can go to things that are beyond linear response, like full counting statistics, which I can tell you about in questions if you care about that. But okay, so let me just quickly jump to my global summary, which is that we now understand a fair amount about what these coherent quasi-particles do at high temperatures in integrable systems. And they give you a wealth of quite interesting transport phenomena, both at the integrable point and if you weakly break integrability. So that's probably a good point for me to stop. So let me stop and take questions.
Thank you, Sarang, for this excellent seminar. Let us thank our speaker. And we are open for questions. So perhaps let me start. You were mentioning in the, when you were showing Kubo formula, right? You were mentioning the whole family, ballistic, diffusive, and everything. So I know in some non-interacting lattice systems, you can go also super ballistic. So can you comment on that? Or also, is it possible in interacting systems to have super ballistic?
If the model has long-range interactions in space, then yes, there's no obstruction. Basically, if you have a model with sufficiently local interactions, say, fall off with space faster than 1 over distance squared, then you have a Lieb-Robinson theorem. And so that means that nothing faster than ballistic transport is permitted. But if you have long enough range interactions, like an all-to-all model, then you can have ballistic transport in both the non-interacting and the interacting case. Basically, what that is in my view, best understood as saying the model doesn't have conventional locality properties.
So is there any integrable model like that?
The sort of kind of trivial examples, I would say, but like not any interesting examples. The trivial examples are basically models with infinite range interactions. So in those models, there's no notion of ballistic because there's no notion of space. So those models are sort of trivially superballistic because everything is connected to everything else.
So that would be SYK or?
Yeah, so for example, you want to talk about SY, I mean, the SYK is really chaotic, but like if you want to talk about, say, the Richardson model of a superconductor or a Godin model of a magnet, like those are examples of something where you're integrable, but you're not spatially local, so you can have correlation functions that are at infinite distance that I don't know, turn on immediately.
Okay, thank you. Do we have any other questions from the audience? Sergey, please go ahead.
Yeah, I just have a question. Did I understand it correctly that you have an integrable system and still see normal diffusion in that?
Yeah, that's that. In some ways, that's surprising, right?
Right. And now, okay, good. Thanks. Yes, so I did get it right. So now my next question is that in any way related to, how should I say that? You see, if I look at integrable systems which are in a different way defined for classical dynamics, I could talk about things like thermalization on a torus for a system with many degrees of freedom, and is that something similar which we talk here about? So then I would also see, in some sense, I won't say diffusion, but I would say at least I see thermalization, so to say, of certain observables. Despite the fact that my system is well defined as an integrable one, has whatever n integrals of motion with n degrees of freedom, etc., and still I can find bunches of observables which will show kind of nice Gibbs-like thermalization. Is that something related?
I think those are two slightly. I mean, I think that's an interesting question. I think those are two slightly different issues. So here, notice that right. So there are two questions: there's thermalization, there's transport, right? So so thermalization is really a question about the equilibrium state and like how you and what it looks like. And so in all of these spin chains that I know of, local observables, most local observables do actually thermalize in the way you're suggesting. Throughout the state diagram, they thermalize. And you need to find fairly special observables to actually notice the integrability.
Okay.
So in that sense, the fact that local operators in integrable systems most of the time obey ETH is sort of it's sort of understood even for free fermion type systems, and it's not too surprising. The thing that's kind of weird here, I think, is like a bit different, because you'll notice that energy transport is ballistic, but spin transport is diffusive. And so what that's saying is that the quasi-particles of this interacting integrable system somehow became neutral under the spin observable. Right, so it's like...
What does that mean, became neutral?
So in the sense that right, so the way I like to explain it is basically using this picture. So, here's my magnon, right? It spends it spends half its time as an upspin, a down domain, and it spends the other half of its time as a downspin, an up domain. So on average, it's not carrying any spin. So it does not contribute to spin transport. And this is a property that you would never guess by thinking about a magnon about the ground state, because the ground state's broken the symmetry, so magnon's always either up or always down. So this is a purely thermal screening effect of the spin of the magnon. And that's the essence of why the transport for spin is diffusive in this model. So this it's a very specific mechanism that occurs in a bunch of integrable systems, basically because of symmetry restoration at high temperature.
Thank you.
So I think, I think you shouldn't think about this as a question about thermalization or not, because it really is just a question about these quasi-particles are well defined, but what quantum numbers do they transport? And it turns out that quasi-particles transport some quantum numbers, but don't transport some others. But I think that's the heart of it.
Yeah, but okay, let me maybe continue. So, but then again, diffusion, as you teach us, is also related to a decay of correlations, right?
Yes, that's right.
And so, are there here these correlations decaying?
Yeah, the decaying because basically, for exactly this reason, because the correlation function is decaying because it's being carried by the magnons, and the magnons are losing their spin. So the structure factor looks exactly like it would in regular diffusion. It's got the same Gaussian shape even. But it's a funny mechanism because it's not diffusion because the quasi-particles are getting backscattered. It's more diffusion because the quasi-particles are getting screened.
And is it also somehow tied up to the fact that you do have a one-dimensional system?
Absolutely, yeah. I mean, via the integrability, right? Because I'm not aware of any non-trivial integrable systems in the sense of not being fundamentally free systems in higher dimensions.
I see. Thank you. Just as a very last short comment to save a bit the face of condensed matter physics, which you mentioned at the very beginning of your talk. I think one of the reasons why most of the time we learn condensed matter physics as a low temperature subject, so to say, is because lots of it is related to electrons, which glue everything together in these condensed, in these pieces of condensed matter. And their Fermi temperatures are usually 10 to the 4 Kelvin. So that's why if you look at electronic degrees of freedom, most of the time you really are, even at room temperature, we enjoy low temperature physics, so to say, or we or they.
Yeah, I agree with that. I mean, there's a good reason why we kept doing that particular game for like 40 or 50 years.
Yeah. But then when it comes to other excitations, like spin excitations, things can be already very different, right?
Yeah.
Thank you. Very nice talk.
Thanks.
And we have also questions or comments from Dario. Please go ahead.
Yeah, I mean, it's maybe related to what also Sergey was asking before. I mean, if I understand correctly, all the let's say surprising behavior that you described is essentially related to the fact that when you have often when you have an integrable system, you think, okay, essentially, if I find the right degrees of freedom, this system is free, so nothing particularly suitable is coming out. But essentially, all the game there is that this, let's say, proper degrees of freedom that make the game free are typically not the degrees of freedom that you observe in an experiment. So in terms of the original degrees of freedom, the dynamics is still very much complicated, and you can see, let's say, interesting physics, right? So I think this is, if I understood correctly, this is the essence of the thing, right? That whenever these quasi-particles are not easy enough in terms of the original degrees of freedom.
That's overstating the case a bit. I mean, I think you're morally mostly right, but I think you're overstating your case a bit because they're not just free. They're interacting elastically. And these elastic scattering events are very important, because if these degrees of freedom were just free, then then my magnon would just go through my domain. It wouldn't shift the domain. The Brownian motion is fundamentally an interaction. It's a scattering effect. And so even if you chose your degrees of freedom perfectly, which you kind of did here, it would not be free. So I'll comment that a similar example of a fundamentally interaction effect in an integrable system is this logarithmic growth of entanglement in the MBL phase.
Right.
Where once again, like you can think about the MBL phase as fundamentally just non-interacting, or mutually commuting degrees of freedom. But at some level, those Hartree type interactions do matter. So elastic collisions, we're used to thinking about elastic collisions in one dimension, or like forward scattering, as being a boring thing that just goes into a normalization of parameters. But that's again like a sort of low temperature intuition that you shouldn't use at high temperatures. With high temperatures, even forward scattering can give you sort of a lot of randomness, because you're scattering, with a random ensemble of stuff.
Okay, essentially you say because these random scattering are for let's say domain walls that are relatively small and so on. So essentially they create. Okay, good.
Yeah, I mean, the way I think about it is that you're trying to go from point A to point B, right? So it's like you spend your time either moving forward or being stuck in traffic. And so if you're at zero temperature, it's like you keep getting green lights, so you keep moving forward. And all the stuff is boring. But if you're at high temperature, then half the time you're sort of stuck in traffic. And so the actual propagator becomes fairly broadened. And that's a quantitatively and even qualitatively important effect.
Okay, thanks. Yeah.
Sergey?
Back to this picture. So then again, if I think about this this chain, let's say with periodic boundary conditions, not so important probably, but then I have a certain set of my black domains, let's say, and then I have a certain set of magnons. Let's just have such an initial state, so to say. And then if all the magnons move in the same direction, then actually I have some kind of some superfluid, right? So everything will move always in the same direction. So then actually I don't see any diffusion in this case, right?
Yeah, that's right. I mean, so that's a zero entropy state, and in general, in zero entropy states, this entire picture breaks down.
It's zero entropy. You might say that, but still, I have lots of degrees of freedom. I can place my magnons in different, positions relative to each other, as long as they don't see each other.
That's fair. So as long as they're moving the same direction, you're saying.
Right.
Yeah. So I think that so in that case, so I think that okay. So let me try and disentangle two issues in what you said. Two issues you brought up. The first is that if you have a finite system on a ring or something like that, then at some point your domains are going to have seen all the magnons, and so your later scattering events are going to be correlated to the earlier scattering events. And so this diffusion picture is going to break down or get severely modified in ways that we're still working out. But so that's one issue.
Yeah, forget about the finite system size. Let's make it.
Now let me get the other issue, which is what happens if you just have all your magnons moving in the same direction, right? So in that case, actually, what happens is that is kind of interesting, because you have this sort of counterflow. Your magnons are all moving right, and your domains are all moving left in the opposite directions of magnons. And so you could ask, well, what actually happens in that regime, and in fact, the sort of amusing fact is that at finite times you still get some diffusion from the sort of random times of the collisions, the random times at which the magnons are colliding with the big domains.
Okay.
So at any given time, some magnons are in white domains, some magnons are in black domains, and that entropy gives you diffusion. But again, yeah, you'd have a low temperature state where these things arrange uniformly, and then you wouldn't get diffusion. So diffusion is fundamentally, in this case, because of elastic events, but they're sort of random. And this randomness is very important because that's where the square root comes from.
Right. Thank you.
Thanks.
Okay, do we have any other questions from the audience? Seems not. So let us thank Sarang again.
Thank you very much.
And with this, we conclude our